Hello, and thank you for joining me today as we continue our discussion on chemical kinetics. Today we're going to talk about the reaction rate, or rate of reaction. And so whenever we're talking about a rate, we are looking at a change in some sort of quantity over a period of time. In this case, we're looking at a change in concentration. So the triangle in this little setup here means change in, the brackets mean concentration, molar value. So change in molar concentration divided by your change in little t is time. And we can measure different types of rates. We can find the average rate, which we'll talk about. We can find the instantaneous rate, which is a little bit harder. And we can find the initial rate, which is your time at, or your rate at t equals 0. And so we're going to look at these three here shortly. So first, when you're looking at following reaction rates, you can find how fast a sample is changing, so how quickly something is becoming something else. In this example here, I'll give you a better picture on the next screen, but this example is looking at 1-chlorobutane here reacting with water and forming 1-butanol, which is here, and hydrochloric acid. But this is looking at your rate of reaction. So we have different times on this side, and we have different concentrations of your 1-chlorobutane. And then we can calculate the change in molar per second is what we're changing in. And so here's a better look at that information. Maybe a better look. So this is showing you at t equals 0, I had 0.1 molar for a concentration. After 50 seconds, my concentration was 0.0905. And so my rate in molar per second, so if I subtract those two, I would get a rate of 1.9 times 10 to the minus 4th molar per second here. That's how quickly it's changing. And so that is our rate of reaction. But it shows you this all the way down until eventually you get to this point where all of it has reacted and you no longer have your initial reactant. You don't have your 1-chlorobutane anymore. And that was after, in this case, 10,000 seconds. So it took a very long time to get to that point. But all right, let's look a little bit more at some other pieces of information. So this is that same graph. This is the exact or same table. And you can find your average rate by calculating your change in 1-chlorobutane by your change in time, which is what they've done here. And so your table is showing you your average rate between those two time intervals. So from 0 to 50 seconds, the average rate is 1.9 times 10 to the minus 4th. For 50 to 100 seconds, the average rate is 1.7 times 10 to the minus 4th. And so on and so forth. You notice it changes. It's going down as your concentration gets smaller. The reaction takes place at a slower pace. And so we can take this information in a data table, and then we can put it on a graph. And graphs are a little bit easier to see and kind of understand and interpret. So this is a graph. I'll show you a picture of this graph here in a couple of seconds, or in a little bit. I have a bigger picture, better picture of this same graph. But we can plot the data from a data table and give us more information about what's going on. So this is much easier to see. You can see based on the slope of the line that here we have a faster reaction. It's happening quicker because it's a steeper line than down here where it flattens out. And so your slope of the curve at one point gives you your instantaneous rate. And so to do that, you would need to use calculus to solve for which is an infinitely small gap between points. That'll give you your instantaneous rate. At t equals 0, again, this is your initial rate. Your instantaneous rate at t equals 0 is typically it's the greatest quantity because it decreases with your concentration dropping. This is the one that a lot of chemists are most interested in. They want to add it right at the beginning, what is my rate? So this can show you the instantaneous and initial rate of the sample in the last page. And again, let me talk one more slide and I'll give you a better graph of it so you can see it and we can talk about it. So that was instantaneous and initial. We also have relative. So rates are followed using a reactant or a product. And so the rate is going to be relative to that one substance. And so the question is, does this give the same rate for each reactant and product? And the answer to that is dependent on stoichiometry. If your stoichiometric coefficients are the same, your rate is going to be the same. But so in this case, when we followed your 1-chlorobutanol and compared it to the use of 1-chlorobutanol, so as this was used up, how much 1-butanol did we produce? These values are going to be the same because in the reaction they had coefficients of 1. But because one is going up, one is going down, they're going to have opposite signs. So down here you see the negative, the drop change in concentration for your 1-chlorobutane is the same as your increase in concentration of 1-butanol. And so one goes up, the other goes down because this one is being used up and this one is being produced. So your signs should match that information there. Here's a better picture of that graph I was telling you about. Let's see if we can make it so we can see the whole thing. So here's another picture of that same graph. So again, here's your coefficients. You see that they are, I have one here, I have one there, and I have one here, and I have one here. Because everything is the same, my rate's going to be the same for use and production. But this is going to be the point that we care about. I want to know this rate here at t equals 0, and then you'll notice this rate changes. And you're just finding the average here. So at 600 seconds, we can find the average by finding the slope of this line. And to do that, you find a line that's tangent to your curve. So that's the same in both cases. But that is how you find your instantaneous rate, is finding the point that is tangent to the curve in the line. Most easily done with calculus, but can be done doing it this way, provided your graph is accurate. All right. We're looking at rates. Relative rates and stoichiometry. We can look at comparisons. So in this case, what if in the above one with the 1-chlorobutane becoming 1-butanol was a 1-to-1 ratio? But what if it's not? So in this case, what are the relative rates for 2O3, which is ozone, producing 3O2, which is oxygen gas? And so what this is telling me is that I'm taking 2 moles of ozone and I am producing 3 moles of oxygen gas. As a quick little, just mentally in your head, if I have to lose 2 moles of this and I have to produce 3 moles of this, which rate has to be faster? Does it have to go faster to lose 2 or to gain 3? Well, the 3 is going to be your answer. Your rate has to be quicker for the production of oxygen. Has to be faster because you're producing this at a higher rate than you are losing the O2 or the O3, the ozone. And so your rate in this case can be -1/2 of your concentration of O3 times change in time, divided by change in time, and then this is going to be 1/3 times your change in concentration of O2 divided by your change in time. And we're going to do some practice with this, so don't panic yet. And what we can do is we can look at how the concentration of a reactant changes the rate of the reaction. And so we can determine the effect that changing the concentration of each reactant has on the rate of the reaction. And how we do that is you run multiple experiments, essentially. If you keep every concentration constant, except for one, you can see what your reaction rate, how your reaction proceeds. You can measure concentrations throughout and get your reaction rate. Then you'll run it again, and you'll change a different reactant, and so on and so forth, until you've done it with each reactant and you can see how each one affects the rate of reaction. So in this case, I'll show you a better picture of this data table on the next page. But this is looking at how ammonium and nitrite react when placed in water. And so experiments 1 through 3 here, which is going to be the same on the next slide, show you a change in ammonium and what happens to the rate of the reaction over here. And then in experiments 4 through 6, these bottom 3, we're going to change the concentration of nitrite, and we're going to see what happens to the reaction of the water. This is going to give us our rate law, which we'll talk about later on. And our rate law shows the relationship between the rate and the concentration for all reactants. We're going to talk about that. Okay, but for now, this is a better, I put it in the screen, a better graphic to show you how concentration changes, or how your rate changes with concentration. So in this case, again, like it was said in the last slide, these first three reactions were changing the concentration of ammonium. So this is my initial concentration. We started at 0.01 molar, we went to 0.02 molar, we ended at 0.04 molar. Notice my concentrations of nitrite are all the same at 0.2. So we're looking for the initial rate in molar per second. With my 0.1, we got 5.4 times 10 to the minus 7th. We got 10.8 times 10 to the minus 7th. We got 21.5 times 10 to the minus 7th. Now, if I flip it and I hold ammonium the same, and I change my concentration of nitrite, now I can see what happens this way. You'll notice they start with a little bit different numbers, but you'll still see the same change. So we started, initially we had a 10.8 times 10 to the minus 7th. We got to 21.6 times 10 to the minus 7th, and we ended at 43.3 times 10 to the minus 7th. So you can look at how those differ accordingly. And that is looking at how concentrations of reactants change the rate of the reaction overall. When we do this, what we're looking for is the rate law, because what has been discovered is that different reactions have different rates. They change in different ways. And so your exponents tell the order of the reaction in respect to each reactant. For example, we had K, which is our reactant rate constant, K times your concentration of ammonium times your concentration of nitrite. Because these are both raised to the power of 1, this is going to be a first order reaction for ammonium and a first order reaction for nitrite. So again, each reactant has a rate order of 1. So it's first order for both of those. Now if I'm looking at the reaction as a whole, my reaction is second order, because I take my exponents and I add them together. So 1 plus 1 equals 2. You add up your reactant orders to get the reaction's total order. So if this is first order and this is first order, the reaction as a whole is second. If this were to be first order and this were to be second order, my reaction would be third order. And that is, we're going to work on this, we're going to look at this in the coming days. But K is your rate constant. It depends on temperature, because remember, temperature is one of those things that affects the rate of reaction. So K is temperature dependent, but that is what we're going to start looking at here. We will get to that next time. Thank you very much for joining me today, and I look forward to working with you next time.